Today's topic is SAP-1 Architecture. The SAP full form is simple as possible, SAP. The SAP is designed for the beginner. The main purpose of SAP is to introduce all the crucial ideas behind computer operation in simple form. SAP-1 is the first stage in the evolution towards modern computers. So SAP-1, it is simplest kind of computer. First important topic is its architecture. Architecture of SAP-1. This figure shows the architecture of SAP-1. It is a bus organized computer. All register outputs to the W bus are 3 state. This allows orderly transfer of data. All other register outputs are 2 state. These outputs continuously drive the boxes to which they are connected. In this figure, architecture of SAP-1 is shown. It is bus organized computer. In the middle, it is the W bus. In this diagram, this W bus is a group of 8 wires. Bus means group of wires. If it is a group of 8 wires, then it can carry a binary word of 8 bits. Some parts are on its left side and some parts are on its right side of this W bus. In left side, first of all, the first box shows the first part, which is program counter. Below this, it is input and MAR. Then 16 into 8 RAM memory. Then instruction register. Then controller sequencer, which produces a 12-bit word. These 12 bits are shown here. These are the boxes on left side of this W bus. On right side of this W bus, the boxes, the main parts of SAP-1 are accumulator A. It is a register known as accumulator. Then adder subtractor, then B register, then output register, and at last binary display. So these are the main parts of SAP-1. This figure shows architecture or structure of SAP-1, which is a bus organized computer. All register outputs to the W bus are 3 state. These are the registers on left and right side of this W bus. And some outputs are shown from these registers to W bus. These are 3 state outputs. 3 state output means we can control that when we want to send a 8-bit word or 4-bit word to this W bus, then we can send it by a particular operation. So the register outputs to W bus or from W bus to these registers are 3 states. We can control these signals. Whenever we want to send a binary word from a register to this W bus, we can send by a particular operation. Or now we consider all these parts: program counter, input and MAR, RAM, instruction register, controller sequencer, accumulator means A register, adder subtractor, B register, output register, and binary display. This controller sequencer produces this 12-bit word. These 12 bits are shown here, and this also produces these 4 signals. CLK means clock, CLK bar, CLR means clear, and CLR bar. Clock, clock bar, clear, clear bar. These 4 signals are also produced by this controller sequencer along with this 12-bit control signal word. And these signals, clock, clock bar, clear, clear bar, are used by these different parts of this SAP-1. As we see here in program counter, there are 4 inputs: CP, CLK bar, CLR bar, and EP. CLK bar means clock bar. It is a clock signal. And when we write bar, it means it is active when it is low. So when CLK bar is low, then a clock signal is given to this program counter. Similarly, when this clear bar, CLR bar, it is active when it is low, then it does the function of clear. Here it is clock signal. It is active when clock is 1. It is given to input and MAR. Here also we have clock and clear signals to instruction register. And there are clock signals here to A register, B register, output register. So these clock bar, clear bar signals are obtained from this controller sequencer. Now, first part is program counter. First part of SAP-1 architecture, program counter. The program is stored in the beginning of the memory with the first instruction at binary address 0000. The second instruction at binary address 0001, and so on. The program counter, which is the part of control unit, it counts from 0000 to 1111. It sends to the memory the address of the next instruction to be fetched and executed. So the instructions are stored at a particular address between 0000 to 1111, and program counter send this address to memory. The program counter is reset to 0000 before each computer run. When computer run begins, the program counter sends address 0000 to the memory. The program counter is then incremented to get 0001. After the first instruction is fetched and executed, the program counter sends address 0001 to the memory. The program counter is then incremented to get 0010, which is equivalent to 2. After the second instruction is fetched and executed, the program counter sends address 0010 to the memory. This process repeats until the last instruction in the address 1111 is fetched and executed. Next part is input and MAR. Below this program counter, this box shows input and MAR. Below the program counter, there is input and MAR block. Input unit includes the address and data switch registers. It sends 4 address bits and 8 data bits to the RAM. Input and MAR is shown here. It has data switch registers and it sends 4 address bits and 8 data bits to the RAM. Look here. There are 4 bits and 4 bits goes from input and MAR to RAM. 4 are address bits and 4, these 8 are data bits, and this goes to RAM. Instruction and data words are written into the RAM before a computer run. MAR means memory address register. It is a part of SAP-1 memory. During a computer run, the address in the program counter is latched into the MAR. A bit later, MAR applies this 4-bit address to the RAM, where a read operation is performed. Next part is RAM. The RAM is a 16x8 static TTL memory, random access memory. Instruction and data words are written in it before a computer run by using address and data switch registers. During a computer run, the RAM receives 4-bit addresses from the MAR and a read operation is performed. In this way, the instruction or the data word stored in the RAM is placed on the W bus for use in some other part of the computer. Next part is instruction register. The instruction register, it is below this RAM. there is instruction register. It receives 8-bit word from W bus and 4-bit words goes to W bus and 4-bit goes to controller sequencer from this instruction register. Instruction register. The instruction register is part of control unit to fetch an instruction from the memory. The computer does a memory read operation. This places the contents of the addressed memory location on the W bus. At the same time, the instruction register is set up for loading on the next positive clock edge. The contents of the instruction register are split into two nibbles. The upper nibble is a 2-state output that goes directly to the controller sequencer. Upper nibble is this 4 bits word that goes to controller sequencer. It is 2-state output, directly goes to controller sequencer. The contents of the instruction register are split into two nibbles. The upper nibble is a 2-state output that goes directly to the controller sequencer. The lower nibble is a 3-state output that is read onto the W bus when needed. Lower nibble is this 4-state output which is connected to the W bus. Next part is controller sequencer. Below the instruction register there is controller sequencer. From this a clear bar signal is sent to the program counter and a clear signal to the instruction register. This controller sequencer produces these signals: clock, clock bar, clear, clear bar. Clock bar signal goes here to program counter and clock signal to input and MAR. Clock signal and clear signal goes here to instruction register. These are obtained all from here controller sequencer: clock, clock bar, clear, clear bar. Below the instruction register there is controller sequencer. From this a clear bar signal is sent to the program counter and a clear signal to the instruction register. This resets the program counter to 0000. The function of clear signal or clear bar signal is to reset to this initial word 0000 and wipes out the last instruction in the instruction register. A clock signal CLK is sent to all buffer registers which synchronizes the operation of computer. A CLR bar, clear bar signal is also sent to the program counter. The 12 bits that come out of the controller sequencer form a word controlling the rest of the computer. The 12 wires carrying the control word are called the control bus. The control word has the format of this: CON, control word. It is a 12-bit word. 12 bits are CP, EP, LM bar, CE bar, LI bar, EI bar, LA bar, EA, SU, EU, LB bar, LO bar. This comes from here. CP and EP. This comes from program counter. Then LM bar from input and MAR. LM bar, M for MAR. L means load, load MAR. And bar means it is active when it is 0. LM bar is active when LM bar is 0. Then CE bar, it is input signal to RAM. CE means chip enable. It is active when CE bar is 0. Then LI bar, EI bar from instruction register. I for instruction register. LI bar, L means load, LI means load instruction register. LI bar is active when LI bar is 0. EI bar, enable instruction register. E means enable, I means instruction register. EI bar is active when EI bar is 0. So CP, EP, LM bar, CE bar, LI bar, EI bar. These 6 bits comes from this left side. CP, EP, LM bar, CE bar, LI bar, EI bar. Then next 6 bits comes from right side. LA bar from accumulator A. LA load accumulator. LA bar is active when LA bar is 0. EA enable accumulator. SU it is signal to adder subtractor. SU is for subtraction. When it is active, then it works as subtractor. SU, EU. SU, EU are from adder subtractor. EU means enable this adder subtractor. Then LB bar, LO bar. LB bar load B register. LO bar load output register. These are 12 bits. Form this control word, CON, control word of 12 bits. 12 bits comes from all these parts of SAP-1. And this control the operation of this entire computer. This word will determine how the registers will react to the next positive clock edge. For example, a high EP and a low LM bar mean that contents of the program counter are latched into the MAR on next positive clock edge. High EP and low LM bar. This is second and third bits, EP and LM bar. EP is active when EP is high and LM bar is active when it is low. So when EP and LM bar both are active, high EP and low LM bar, when EP is high, E means enable, P is for program counter, enable program counter. If it is active, then a 4-bit word goes to W bus. 4-bit word from program counter, which is address from 0000 to 1111. It goes to this W bus when EP is active, when EP is high, EP is 1. And from W bus it goes to input and MAR only when LM bar is active. When LM bar is active, load MAR, then this 4-bit word from W bus comes to input and MAR. So when we want a 4-bit word from program counter to input and MAR, then this first this 4-bit word goes to W bus from program counter, and it goes when EP is active, when EP is 1. And from W bus this 4-bit word comes into MAR only when LM bar is active. Load MAR, and LM bar is active when it is low. All the bits which have bar, these are active when these are low, and all bits which are without bar, that are active when they are high, they are 1. Similarly, a low CE bar and a low LA bar. Low CE bar and low LA bar means these two are active, CE bar and LA bar. This means that the addressed RAM word will be transferred to the accumulator A on next positive clock edge. When we want to send a addressed RAM word, a word stored in RAM at a particular memory location, and if we want to transfer it to the accumulator A, then we have to make this CE bar active, and CE bar is active when CE bar is low. When CE bar is active, CE bar is here connected to RAM. When it is active, then the word which is stored in this RAM at a particular memory location, it goes to W bus. This is the 8-bit word going from RAM to this W bus. This goes to W bus from RAM only when CE bar is active, when CE bar is low, chip enable. And from this W bus, if we want to take this 8-bit word to this accumulator A, then we have to make this LA bar active, load accumulator. We want to load this accumulator by this 8-bit word. So for this we have to active this LA bar when LA bar is 0. So if we want to send a addressed word from RAM to accumulator A, we have first make this CE bar active, means we have to put this CE bar at 0, low, and then we have to put this LA bar equal to 0, low, or LA bar is active. Then this accumulator is loaded by that 8-bit word. In this way, this controller sequencer, which produces a 12-bit word, it controls the operation of all these parts. Next part is accumulator. The accumulator A, it is a buffer register that stores intermediate answers during a computer run. It has two outputs, The two-state output goes directly to the adder subtractor. This is the accumulator. It is buffer register, register A. Below this is adder subtractor, and below this adder subtractor we have another buffer register, register B. So we have two registers, register A and register B, and adder subtractor is in between these two registers. Register A is known as accumulator. It stores intermediate answers. This 8-bit word which goes from accumulator A to adder subtractor, it is a two-state, it is directly connected to adder subtractor. And this 8-bit word which goes to W bus, it is a 3-state output, and this goes to W bus only when this EA is active, enable A. When EA is 1, then this 8-bit word goes to W bus. So this is 3-state output which goes to W bus, and this is 2-state output which goes to adder subtractor, and it goes directly to adder subtractor. So it is 2-state, and this 8-bit word which goes to W bus, it is 3-state output. It goes only when we want, when EA is active only. When EA is 1, then it goes to this W bus. The 8-bit accumulator word continuously drive the adder subtractor. The same word appears on the W bus when EA is high. Next part is adder subtractor. Below this accumulator A, we have adder subtractor. SAP-1 uses 2's complement adder subtractor. When SU is low, the sum out of the adder subtractor is S equal to A plus B. A is word in A register, that is accumulator, and B is word in B register. When SU is low, this is the adder subtractor. SU means subtraction. When SU is active, when SU is 1, then it works as subtractor, it subtracts, and when SU is low, then it works as adder. So if we want to add two words, then we have to put SU equal to 0. SU is low, then it works as adder, and we will add the two words from accumulator A and B register, and we get sum S equal to A plus B. When SU is high, the difference out of the adder subtractor is S equal to A plus B dash equal to A minus B. B dash is 2's complement of B, and it is equivalent to decimal sign change. So when SU is high, it works as subtractor, and the resultant word S is A minus B, and when SU is low, then it works as adder, and the word is S equal to A plus B. The adder subtractor is asynchronous, unclocked, so its contents changes as soon as the input words change. When EU is high, these contents appear on the W bus. So adder subtractor either add or subtract these two words from A and B register, and this addition or subtraction, this result goes to W bus only when this EU is high. E means enable, U is for adder subtractor. Then we have B register. B register is another buffer register. It is used in arithmetic operations. A low LB bar and a positive clock edge load the word on the W bus into the B register. The two-state output goes directly to the adder subtractor. It supplies the number to be added or subtracted from the content of accumulator A. If we want to add or subtract, we need two words. One is stored in accumulator A and other is stored in this B register. So we have two words. Word A is in accumulator A, word B is in register B. When LB bar is active, which means LB bar is 0, LB means load B register. It is active when LB bar is 0, it means load B register. Then B register is loaded by the word which is on this W bus. And we have this two-state output which goes directly to adder subtractor. Then this 8-bit word which comes from this W bus, this goes directly to adder subtractor where add or addition or subtraction operation is performed, and then the resultant word goes to accumulator A. So this is B register. After that we have output register. The output register is often called an output port because processed data can leave computer through this register. At the end of a computer run, the accumulator contains the answer to the problem being solved. When EA is high and LO bar is low, the next positive clock edge loads the accumulator word into output register. If we have performed some operation like addition or subtraction, then the result is stored in the accumulator, and we want this result which is stored in accumulator, we want this word into this output register. So first of all we have make this EA active, enable A register. When EA is active, it means when EA is 1, then the accumulator content goes to this W bus, and from this W bus this word will come to this output register only when this LO bar is active, load output. LO bar is active when LO bar is 0, then the result from accumulator now comes into this output register. The output register is often called an output port because processed data can leave the computer through this register. At the end of computer run, the accumulator contains the answer to the problem being solved. When EA is high and LO bar is low, the next positive clock edge loads the accumulator word into the output register. Then we have last part of SAP-1, it is binary display. The binary display is a row of 8 light emitting diodes, 8 LEDs. Each LED is connected to one flip-flop of the output port, so it shows the contents of the output port. After we have transferred an answer from accumulator to the output port, We can see the answer in the binary form by using this binary display. Summary: the SAP-1 control unit consists of program counter, instruction register, and the controller sequencer that produces the control word, the clear signals and clock signals. Its arithmetic logic unit ALU consists of an accumulator, adder subtractor and B register. The SAP-1 memory has MAR and RAM. The input-output units IO units includes the input programming switches, the output port and binary display. So this is the SAP-1 architecture.